Today's power plants are extremely complex, and operating them can be a demanding job. As an operator, you're responsible for many things, including maintaining power production and making sure that your plant operates safely and efficiently. To see why this is important, it's helpful to know how your plant fits into a power system that provides electricity and distributes it to customers. The purpose of all power plants is to generate electric power. A power plant, or power station as it's sometimes called, generates electricity from one of several possible sources of energy. For example, fossil fuel plants use coal, oil, or natural gas. Nuclear plants use uranium, and hydroelectric plants use water stored behind dams. A power plant releases energy from one of these sources and converts it to mechanical energy that drives an electric generator. The function of the generator is to convert mechanical energy into electrical energy. A power plant may have 2, 3, or even more generators producing electricity at the same time. Each generator, together with the equipment that it requires to make electricity, is typically referred to as a unit. The amount of electricity that a generator produces is commonly measured in watts. The generators in most power plants are capable of generating millions of watts of electric power. 1,000,000 watts is a megawatt. To get a better understanding of how a power plant is tied to its customers, we'll take a look at how electricity can be transmitted and distributed to individual customers. As we look at an example, we'll concentrate on the basic parts of a power system. The electricity produced by each generator in a power plant goes first to the unit transformer that the generator is connected to. A transformer is an electrical device that can raise or lower the voltage of electricity. Voltage can be thought of as a kind of electrical pressure. It's the driving force that causes electricity to flow. The unit transformers increase the voltage of the electricity leaving the power plant. Raising the voltage allows the electricity to be transmitted more efficiently. The switches that open and close electrical circuits to connect the generators to transmission lines and their related equipment are in an enclosed area referred to as a switchyard. The transmission lines transmit the output of the generators to the areas where the utilities' customers are. A facility called a substation uses transformers to decrease high transmission voltage to a voltage that can be used locally. In some substations, electric power from several sources is combined before it is routed to the customers. The electricity is then distributed to nearby neighborhoods on local distribution lines. These lines are either attached to utility poles or buried underground. When the electricity reaches its destination, another transformer decreases the voltage again so that it's compatible with the customer's appliances and other electrical equipment. We've just seen how electricity flows from a power plant to the customers who use the electricity. In reality, most power companies own several plants that are connected together to form a system. The combination of all of the plants, switchyards, substations, and transmission and distribution lines is called a power system. One company's power system is often tied to other power systems to create a network called a power grid. A power grid provides a large, reliable source of electrical power. The electricity used in homes and factories is alternating current, or AC. This type of electricity can't be easily stored. It has to be supplied when it's needed. In other words, when any electrical device is turned on, it creates a load on the system, and the power to run the device must be immediately available. The amount of electric power needed by a power system's customers is called demand. Whenever demand increases, the amount of electricity being supplied must be increased to satisfy the increase in demand. The amount of electricity produced must always equal the demand for electricity. As you can imagine, meeting the demand for electricity can be a complicated operation. People are constantly turning machinery, lights, and appliances on and off. Fortunately, most power systems are able to handle these changes in demand. Often, when one piece of equipment is being turned on, another is being turned off. When this happens, demand is relatively constant. Over the course of a 24-hour day, however, demand can change quite a bit. When do you think demand is usually lowest? Demand is usually lowest at night, when most businesses are closed and most people are sleeping. Demand increases in the morning when people get up and businesses start to open. The peak in demand often occurs in the early evening hours when many people are returning home from work and some businesses are still open. Since the demand for electricity is constantly changing, someone must ensure that production and demand remain equal. This is the job of the load dispatcher. The load dispatcher predicts the demand for electricity and monitors the condition of the power system. The load dispatcher also coordinates the outputs of all the power plants in the system so that supply will equal demand. We'll use this example to get a better idea of how load dispatchers do their job. In this power system, there are 4 power plants. The first power plant is a hydroelectric plant. Its energy source is water stored behind a dam. Since this plant doesn't use a fuel that costs money, it's the least expensive to run. The second plant burns natural gas. It's the newest and most efficient plant in the system. The third and fourth plants burn oil and coal. They are the oldest and least efficient plants in the system. Together, the 4 plants supply electricity to customers in a large city. On a typical day, the load dispatcher has the hydroelectric plant and the gas-fired plant operating near their maximum capacities. Why do you think the dispatcher does that? On a typical day, the load dispatcher has the hydroelectric plant and the gas-fired plant operating near their maximum capacities because they produce the cheapest power. The oil and coal-fired plants, which are less efficient, are operating at lower capacities. The load dispatcher meets increases in demand by increasing the load on the oil and coal-fired plants. As demand decreases, he reduces the load on the oil and coal-fired plants first, since they cost the most to operate. The load dispatcher must also know what to do if a problem occurs. For instance, like other machinery, the equipment and generating unit sometimes breaks down. When a unit breaks down, the immediate problem is replacing the lost power. The first thing the load dispatcher does in response to this kind of problem is increase the load on any unit that was not operating at its maximum capacity. If this doesn't meet the demand for electricity, the load dispatcher will usually try to buy additional power from neighboring power companies. If the neighboring power companies can't supply the power needed to match the demand, the load dispatcher must cut off some of the customers to reduce the demand. If demand isn't reduced, the operating units would be overloaded and they could be damaged. In this topic, we looked at how power plants generate electricity. We saw how electricity is distributed to customers, and we saw how demand can affect a power plant's operation. Now let's try some practice questions on this material. A power plant releases energy from its fuel and converts it to mechanical energy that drives an electric generator. The function of the generator is to convert mechanical energy into electrical energy. The switches that open and close electrical circuits to connect the generators to transmission lines and their related equipment are in an enclosed area referred to as a switchyard. Since the demand for electricity is constantly changing, someone must ensure that production and demand remain equal. This is the job of the load dispatcher. The energy conversions that take place inside a fossil fuel plant change the energy stored in coal, oil, or natural gas into electricity. The term fossil fuel refers to the fact that the sources of the fuels are the fossilized remains of plants and animals. Most of the energy conversions take place in 3 main components. These components are the boiler, the steam turbine, and the generator. In a typical fossil fuel plant boiler, the tubes that form the walls of the boiler are filled with water that is under pressure. Fuel is fed into the boiler where it is ignited and burned. As the fuel burns, it releases thermal energy, which is absorbed by the water in the tubes. As the water absorbs the thermal energy, its temperature increases and it begins to boil. The boiling water changes into steam, which is heated even more and then routed out of the boiler and sent to the turbine. So, in the boiler, the energy in fuel is converted into thermal energy, and then the thermal energy goes into the steam that flows out of the boiler. Inside the turbine are 2 kinds of blades. The blades that are attached to the casing are called stationary blades. The blades that are attached to the turbine shaft are called moving blades. When the steam strikes the blades that are attached to the shaft, it causes them to move, which makes the shaft rotate. In the process, some of the energy in the steam is converted into mechanical energy in the turbine. Since the turbine shaft is connected to the generator, this mechanical energy is transferred to the generator. In the generator, the mechanical energy is converted into electricity. The steam that passes through the turbine next enters the condenser. In the condenser, additional energy is removed from the low-pressure, low-temperature steam to cool it and convert it back into water. The water is then pumped through a series of heaters and back to the boiler, where it's used again to produce more steam. The entire steam and water loop, from the boiler, through the turbine, into the condenser, and back to the boiler, is called the steam cycle. Like all power plants, fossil fuel plants have advantages and disadvantages. One of their biggest disadvantages is that fossil fuels are expensive, and companies that operate fossil fuel plants have to keep buying fuel. Another disadvantage of fossil fuel plants is that the exhaust gases produced by burning fuel often contain harmful substances that must be removed before the gases can be released to the environment. Removing these substances can be costly, and it can affect the efficiency of the plant. On the other hand, fossil fuel plants have many advantages. For example, unlike hydroelectric plants, fossil fuel plants aren't required to be located only where a dam can be built. The fuel for most gas turbines is either oil or gas. Gas turbine plants can also be called combustion turbine plants, since the turbine uses gases that are created as a result of combustion. A gas turbine unit uses a series of energy conversions to change the energy stored in its fuel into electricity. Most of the energy conversions take place in the three major components of the unit. These components are the combustor, the turbine, and the generator. The three components are usually assembled as a single machine. Air is drawn into a gas turbine by a compressor. In the compressor, the pressure of the air is increased so that it can be forced into the combustor. Inside the combustor, the compressed air is mixed with fuel, and the mixture is ignited and burned. The burning creates gases that expand rapidly. The energy that is released from the burning fuel is converted into energy in the expanding gases. The gases flow from the combustor into the turbine. In the turbine, the hot gases flow between the blades, where some of the energy in the gases is transferred to the blades. This energy transfer causes the rotor to which the blades are attached to spin, which produces mechanical energy. Since the turbine and the generator are connected, the mechanical energy of the turbine is transferred to the generator, which produces electricity. One major advantage of a gas turbine plant is that the plant can go from a complete shutdown to a full load condition in a matter of minutes. Another advantage that many gas turbine units have is that all of the components are assembled together by the manufacturer. This means that after a gas turbine unit is purchased and delivered, only a small amount of work is required to put it in service. Gas turbine units also have some disadvantages. For instance, many of them are very loud when they're operating, and this may limit the locations where they can be installed. Another disadvantage is that they may be less efficient than fossil fuel plants. The gases that are exhausted from the unit are very hot, and they may still contain a lot of energy. One way that this disadvantage can be overcome is to make the gas turbine unit part of what is called a combined cycle plant. In a combined cycle plant, the exhaust gases from a gas turbine are used to produce steam to drive a steam turbine. The hot exhaust gases that leave the gas turbine are routed to a heat recovery steam generator, or HRSG. In the HRSG, the exhaust gases transfer heat to water to produce steam. The steam that's produced is sent to the steam turbine, where some of the energy in the steam is converted into mechanical energy. The mechanical energy is then converted into electricity by a second generator. This increases the efficiency of the plant, since more of the energy in the gas turbine exhaust gases is used before the gases are released. Hydroelectric plants are some of the simplest power plants available. They use falling water to operate. A dam stores the water that a hydroelectric plant uses to produce electricity. The dam has controls so that the amount of water that flows through the dam can be controlled. The water stored behind the dam has pressure due to the height of the water. This pressure is a form of stored energy. When the water is released by the dam, the pressure forces it through openings in the dam and through the power plant. As the water flows through the plant, it turns several water turbines. So, as the water flows through the plant, the energy of the water is converted into the rotation of the water turbines. A water turbine consists of a series of blades or buckets mounted on a shaft. The shaft is directly connected to a generator. A hydroelectric plant may have several water turbines and generators. The force of the water flowing from the dam pushes against the blades, causing the blades and the shaft to rotate. This creates the mechanical energy that the generator converts into electrical energy. Like all other power plants, hydroelectric plants have advantages and disadvantages. One advantage of a hydroelectric plant is that its design is relatively simple. Also, the water that is used to drive the turbines doesn't have to be purchased. One of the disadvantages of hydroelectric plants is that they can only be built on rivers or lakes that can support a dam. Another disadvantage is that if there's a severe drought, the output from a hydroelectric plant may have to be reduced or the plant may have to be shut down. Of all the different types of power plants, nuclear power plants are probably the most complex. They're similar in design to many fossil fuel plants, but they use a different process to create the thermal energy that is converted into mechanical energy. This is a simplified illustration of one type of a nuclear plant. Its main components are a reactor, a steam generator, a turbine, a generator, and a condenser. The reactor contains the fuel that the plant uses. In most cases, the fuel is uranium. When this plant is operating, the uranium breaks down in a process called nuclear fission. The breakdown of uranium produces fragments of uranium which can be called fission byproducts. As the fuel fissions, it produces energy that is converted into heat. This heat is transferred to water that is flowing through the reactor. The water is under high pressure so that it will not boil and change to steam in the reactor. The heated water is pumped to the steam generator, which is basically a heat exchanger. In the steam generator, the heated water from the reactor passes through tubes and gives up its heat. Water at a lower pressure flows around the tubes and absorbs the heat. What do you think happens to the lower pressure water? When the lower pressure water receives heat, it boils and changes into steam. The steam that is produced in the steam generator is directed to the turbine. The turbine uses blades, both stationary blades and rotating blades, to produce mechanical energy. When the steam hits the rotating blades, it causes them to move, turning the turbine shaft. Some of the energy in the steam is thus converted into mechanical energy. Since the turbine is connected directly to the generator, the mechanical energy of the turbine is transferred to the generator where it's converted into electricity. The steam leaves the turbine and enters the condenser. In the condenser, more energy is removed from the steam, and it's converted back into water. The water is then pumped through a series of heaters and back to the steam generator, where it is boiled again to produce steam. As with all the other types of power plants, nuclear power plants have advantages and disadvantages. For example, one advantage is that the fuel costs of a nuclear plant are less than those of a fossil fuel plant or a gas turbine. Also, a nuclear plant does not create the same forms of air pollution that burning coal or oil creates. Nuclear plants also have some disadvantages. Since they're more complex than other types of plants, they usually cost more to design and construct. Also, fission byproducts that are left over after the fission process are radioactive and require special storage facilities. In this topic, we've looked at how different types of power plants make the energy conversions that produce electricity. We examined typical fossil fuel plants, gas turbine plants, hydroelectric plants, and nuclear plants. Let's stop here and try some practice questions on this material. When the steam strikes the blades that are attached to the shaft, it causes them to move, which makes the shaft rotate. In the process, some of the energy in the steam is converted into mechanical energy in the turbine. Inside the combustor, the compressed air is mixed with fuel, and the mixture is ignited and burned. The burning creates gases that expand rapidly. The energy that is released from the burning fuel is converted into energy in the expanding gases. When the water is released by the dam, the pressure forces it through openings in the dam and through the power plant. As the water flows through the plant, it turns several water turbines. So, as the water flows through the plant, the energy of the water is converted into the rotation of the water turbines. This is a simplified illustration of one type of a nuclear plant. Its main components are a reactor, a steam generator, a turbine, a generator, and a condenser. The reactor contains the fuel that the plant uses. In most cases, the fuel is uranium.